Hey, what's up, guys? This is Cheng here. So today, let's take a look at this problem number 354, Russian doll envelopes. I think some of you may know this Russian doll, right? Basically, so this is like a doll inside another doll, right? Which is another doll, which is another doll. So you have a number of envelopes with width and height given as a pair of integers with W and H. And one envelope can fit into another only if and only if both the width and the height of the one on one envelope is greater than the width than the other one. So it means that we can only fit in one envelope into another one if both the height and weight is strictly smaller than the other one. And then it asks you to find the maximum number of envelopes can you Russian doll, right? Put one inside the other. Note the rotation is not allowed. So and here are some examples. So the first one is you're given like this envelope with this kind of like width and height, and the output is 3 because that's the three envelopes you can fit into each other. Basically 3, 2, you can fit in 4 and 5 because 4 is greater than 2, 5 is greater than 2, and 4 is greater than 3. So that's 2, and another one is 6 and 7, right? Because 6 is greater than 5, and 7 is greater than 4. So, so if you guys watch it closely, as you guys probably already find out, right? So basically, this is like the two strictly increasing sequence here, right? So first one is the width, and the second one is the height. I mean, if you guys have done the problem called the longest increasing subsequences. So this problem it's just like a two two-dimensional version of that longest increasing sequence because both the height and width they are like basically you have to satisfy that longest increasing subsequence in both height and width, right? So and actually this problem is a little bit similar than last week's weekly contest problem, which is I think it's called uh, best team with no conflict, something like that. So but for that problem, it's similar. Basically, you're given like a team with an agent score, and it asks you to find the maximum score without conflict. So basically, it's similar as this one. I mean, so every time when you guys see this kind of like so the longest sub increasing sequence uh, longest increasing sequences with two conditions we need to satisfy, right? So this in this problem is we have to satisfy both the height and width. So every time with this problem, we just need to sort one condition first. We satisfy one conditions, and then we can utilize that longest increasing subsequence logic to get the maximum value based on the other condition here. Okay, so for the so for those who still don't know the logic for the longest increasing subsequence, basically for that one, the basic logic for that one is we have a DP. We have a DP array here, right? So this DP array stands for the longest increasing subsequence with this number at with this number as an ending number. Okay, and then so what do? We simply do this, right? We do a max of what? Max of the DPI, right? So max of DPI and the DPJ plus 1, right? If the number I is greater than the number of j. So that's the LSI logic. Basically, at each of the ith locations, we loop through all the numbers before I, and then we find out all the numbers. For each numbers whose number is smaller than the current I, then we know, okay, so we have find the another valid candidates that we can calculate our current DP, right? So it means that since this DPJ is also strictly increasing, since we have this like conditions for each of the DP, so it means that we have DPI here, right? And then we have some numbers, and then we have a DPJ, right? Because DP from 0 to DPJ, this is increasing, and since DPI since number I is greater than number j, so which means that from 0 to DPI plus and to DPJ, this is also strictly increasing. That's why this thing works. Okay, so that's the basic LIS logic, and we can just simply utilize this method here. Okay, I'll give you guys this straightforward solution first, and then I'll be discussing another solution, because for this problem, if you're using this like kind of like the native LSI solutions, it will TLE. So which means we'll need a better solution for this. Okay, but let me try to implement this one first. Okay, so like I said, since we have two conditions we need to satisfy here, right? So we will be sorting at the first condition. We'll sort on we can sort on anyone, doesn't really matter. So we'll just sort on the width first. Hmm, envelopes. We do a sort. We simply do a sort. Basically, this will sort by the first condition, right? And then we have an nth level here. Okay, envelope. And then we're gonna have like a DP. So for we initialize all the values with DP with 0 and with 1, because at each of the locations, as you guys can see, the envelope itself still counts at 1. So even though we can do this Russian dot twice, but the total number is 3. That's why we start this thing with 1. Or we can initialize everything with 0, and in the end we increase the final answer by 1. Either way is fine, but in this case I'll just initialize with 1. So, and then we have I in the range of n here, right? So now, since we have already sorted by the width first, so it means that the the width is always increasing. No, it's not. It's not increase. It's always non-decreasing. So that's why, like I said, for j here, right? So the range is from 0 to I here, and we need to check basically the envelopes I1. That's basically the height, right? The height is greater than the j's height, then we can do. But there's like one more thing you guys need to be careful here, because it says both the width and height has to be strictly greater. So which means that even though we're sorting by the width already, but the width could be the same, right? So for that case, we cannot consider it's a valid candidate. So which means that basically we have to do this. 0. Okay, so it means that the first one is the height, but still we need to check if the if the width is not the same, because we have already sorted the width here. But so here we are essentially only checking if the width. Let me do this. Yeah, like this. Basically, I'm only checking if the current width is not the same as the previously weight. Then we know, okay, so we can use this one to calculate our current J here, right? So it means that the dpi is equal to the maximum of the dpi, and then from dpj plus 1, because so now we have found another envelope, so that's why we can do another Russian doll here, right? Yeah, and that's it. So in the end, we simply return what? We return the maximum dp. Yeah, so why is that? I mean, this is because, if we have like a bunch of numbers, let's say for the LIS, right? We have a numbers here like the 0, 1, 2, 8, right? And then 2, 3, 4, 6, 9, 10. I mean, basically the longest increasing subsequence could at any location. It could end up here. So that's the first increasing sequence, and this is the second one, which in this case the last one is our final answer. But it's not always true, right? So the longest subsequence could end up at any location. So that's why we have to do a maximum of dp. Yeah. So this thing in terms of the logic wise, I think it is correct. If we run the code, yeah, certainly pass. But if I submit it, it will t. Oh, okay, sorry. Yeah. So of course we need like this. If not envelope, we simply return 0, right? So let me submit one more time. Yeah. So this means TLE. Yeah. So let me check the details. How many? Yeah. So it's almost past everything, but it's still TLE here. So why is that? Because for the traditional LIS, longest increasing subsequence solutions, this is clearly a O(n) square solution, right? And even though it didn't give us the range of the problem, but seems like so this O(n) square solution will fail. Then it leaves out no other choice but to find a better solution, which is the n log n solution of this LIS. Okay. So to do that, let me try to explain these things here for you guys. See if we can have this. Hmm. Okay, I'll just try to explain it here. So let's assuming we have like a bunch of numbers. I'm only trying to solve this LIS problem. Let's say we have a 0, 8, 4, 10, 2, 6, 9, 11. How about this? So if we're trying to solve this longest increasing sequence problem, what is another way to solve this? So a better way is this. Basically, we're maintaining like a DP here, but in this DP here, we're only maintaining the current longest subsequence we can get by this position. So what does it mean? It means that in this DP here, we're always maintaining like a increasing number. So which means that, for example, we have a 0 here. At the beginning, we have 0. Okay. And at 8 here, and every time, since we're maintaining like always increasing numbers here, we can do a binary search. We can do a binary search to find the proper insert location for the new numbers here. Okay, so and based on this location, we'll decide if we will replace update the value or we will append this value. So at the first one, 0, of course it's 0. At number 8 here, we do a binary search, right? So we do a binary search, and then what values we get? We get like, we got 1 here. So 1 is the same as the length of this DP here, right? So it means that, okay, so the 8 is greater than all the numbers in this DP here. So that we will basically we'll append this number to the end of this DP here. And now we have 4, right? So we have 4 here. So what's the what's the index if we do a binary search of 4? It's 1, right? And then basically we'll update 4 here. We'll update 4. So why is that? So why we can update 4? Because 4 is smaller than 8, right? Because 4 is always smaller than 8 because we're doing like the binary search. So it's always guaranteeing that the new numbers at we are having here will be will either equal or smaller than the previously numbers at the same location, and then we can replace that. So this is a little bit like greedy idea behind the scene here, because we have find another number, right, which is smaller than the previous one, so that this one may give us a longer subsequence. So that we have 4 here, and then the next one is 10, right? So the next one is 10. So 10 is what? 10 is okay. So 10 is another one. So 10 is greater than everything. So that's why we append these things to the end. Okay. And now we have 2 here. So what's the index of 2? It's also 1 here because the 2 will be inserted into 1. So now what we do, we update again, right? So we update 1 with 2 to 10. And then what? And then 6, right? We have 6 here. So 6, what's the index of 6? It's 2, right? So which will be here. And we'll be updating that to 0, 6, sorry, 0, 2, and 6. And then we have 9 here. So 9 is greater than everything. So we do a DP equals to 0, 2, 9, 0, 6, and 9, right? And then the last one is 11. Do the same thing. 6, 9, and 11. So basically, within this approach, in the end, the length of DP will be our answer. That's gonna be 5. So as you guys can see now, with this solution, the time complexity will become n log n, right? Because we loop through everything n times, but with each of the loop here, we do a binary search, which is a log n. That's why this solution is much faster. And the key observation for this solution is this append is easier to understand, but the most important part is this replace part. Basically, every time when we have like numbers, we find the index here, we'll be replacing that number with the same index. So why we can do that? Because we are still maintaining like the increasing pattern here, right? Because we do a binary search, we find the place for this new numbers, and after replacing these numbers, we know okay, it still complies with this increasing pattern. That's why we can replace that. Okay. So with this in mind, let's try to use this one for this problem, right? Okay, cool. So for that, let me try to comment out the first one here. I think we can comment out here, right? We'll be needing those sort there. So like I said, we'll be maintaining like an empty DP first, right? And then we'll basically loop through the width and height in the envelopes, right? So we'll first find the index of we'll do a binary search for the current number, which in our case is the height, right? Because we're storing this height in this DP. Okay, and we're doing like the binary search, sorry, left. Sorry, it's not right. It should be left. So why is that? Because the issue with doing a binary search left is because in case of the same numbers here, right? Let's say we have another 8 here. We come after 8, there's another 8. We don't want to append this 8 because remember we have a condition, right? If the current index is smaller than the length, then we do a replace. Otherwise, if it's equal to the length, we do a append. And when there's a same 8 here, we want to get index 1, not 2, because with the left it will give us 1, but if we do a right, it will give us 2, which is not what we want, right? So here, so the logic, like I said, so if the index is smaller than the length of the DP, okay, then we do what? We replace this DP index with the current age, right? Else what? Else we simply append DP append the current age, okay, and then we return the length of DP, right? So these things, this looks promising, but is this one correct with everything here? No. So why is that? So this is because, we are replacing these numbers, right? Since, we have for the 1D, like the regular LIS, after replacing here, right? We have all the numbers in DP still conform, I mean, following the increasing rules here. But here, even though, right, even though we have like this W here, we have W like increased already. But if we're only doing this H here, we have this W we still need to consider here. So I'll give you an example here. You know what? So the best example is just to submit, and this will give us the example here. Okay, so basically that's the example we need here, right? So okay, so if we sort by the by the width and then the height, so what we'll have 1 1, right? So that's and then we have 2 3, and then we have 4 and 5, right? And then we have 4 and 6, and then we have 6 and 7, 6 and 7. Okay, so that's the sortings after that's sorted the list. And this is okay. From 1 to 1, this is okay. which means we will have like what? Let's see. So in this case, we'll have like dp equal to what? Since we remember we're storing this height in the dp here, we'll have 1, 3, and then 5, right? 5. Okay, so we have 1, 3, 5, and then what? And then we have 6, right? But can we use 6? Probably not, because we have this thing. We have the we have this. I mean this width we need to be taken care of, because we cannot, for this 6 here, we cannot 1, 3, 5. We cannot add 6 here, because 5 and 6, they have the same width, right? So which means we cannot simply using these numbers here. So we have to find another way. I mean, someone may think that maybe we can like introducing another, like a width DTH array here, which will be storing the corresponding width for each of the height here. And every time when we do this kind of index, or either insert or update, we check that width. That will not work either. This is because, so every time when we update this height here, will be sorry, when we get the index for this height here, we'll be updating the DP with this height, and we're assuming every time when we update this height here, so both of the conditions should still be maintained, right? But if we're doing that, even though we have the width here, it will never. So the width, the increasing pattern of the width will always be broken. I mean, you guys can try to do it. I already tried, so it won't work. Even though you're trying to tweak this width, do an update, or we check if the width is smaller or greater, and then you do append, it will always broke. It will always break the pattern. So then it only leaves us one option, which is to change the sorting a little bit. So as you guys can see here, so the issue happens right here when we do a 4, 5, and 4, 6, and the issue happens when we have 4 and 4 have the same width, and then if we are sorting this height in the same increasing orders, so we will process this 4, 5 first, and then we'll process this 4, 6. What does it mean? It means that even though the 4, 4 are the same, we're still considering this 5 and 6 a valid increasing sequence. So the easiest way to fix this is that we simply reverse these two sortings here. So now we have 1, 1, 2, 3, and 4, 6, right? So if we follow the below logic here, so we have 1, 3, and 6. Okay, and now we have 4 and 5. Right, so if we have 4 and 5 here, and we do a binary search, instead of 3 here, we'll get 2, which is here. So which means that we'll do an update this time, and the length is still 3. So now the problem is solved. So which that means is that we simply do a customized sorting here. We do a key equals to lambda lambda what? X, and what is the key? So the key is we sort by x0, ascending order, and then we do a sort by the second numbers, descending order, right? So that's the sorting, and that's how we fix this problem here. Okay, so let me try to run the code. Cool. So this thing works and submit. Yeah, as you guys can see, this one is super fast. This is because the time complexity is now unlog n here. Yeah. Yeah, and if you guys know how to solve this problem, instead of doing a reverse sortings here, if you guys can find a way of introducing some additional arrays to solve it, I would love to know it, know that as well. Yep. And other than that, I think it is a great problem. So the first solution is a traditional DP solutions, which is the n square solutions. This one is pretty easy to understand, right? Basically, we try all the previously envelope. Of course, we need to sort first, and then anyone that satisfies the conditions, we can use that as a candidate. And then in the end, we return the maximum number. And the second one here, I mean, in the interview, I'm not sure if the interviewer will ask you to improve your n square solutions. I think 30% of the chance it might happen. So it's at least it's better to know there's like another way of using this DP. Basically, we're maintaining like the DP arrays here, and then we're using a binary search to help us to find the maximum length. So this part, I think it's not that hard to understand, right? Basically, the why this thing works is because first we're maintaining like a length, right? And every time when we find the smaller numbers, when we find the smallest numbers in the comparing with the previously numbers, we update that numbers because we know that once we find a place for that, right? Because basically we're replacing that number with this number because in later on we might find like a different numbers based on this number, right? A greater number based on this number. That's why we will do the update. Okay. Yeah, basically we are as if we are finding a better candidate for this index. Previously we have an index at index 8 here we have sorry at index 1 here we have 8. So now we have 4 here. So now basically the you know the we have better candidates at 4 here. So why is that? Because we have 8 0 8 4. Let's say we have 5 and 6. So we have 0 and 8. We have 4 here. So now we have 4 because 4 is smaller than 8, which means that between 4 and 8 later on, let's say for example in this case, right, we might find a better solutions by using 4 as this at this index. Okay. Yeah, actually speaking of that, we might also be able to use the a mono queue to solve this problem. Something like this. Since we're getting the minimum, sorry, the increasing sequence. I mean, every time when we have a new numbers here, right, we pop anything that is smaller than the current one, and in the end, that's the answer, right? Hmm. So let me try that. This might also work. Interesting. Let me comment out these things here. So basically, this is what I meant here. While the DP is not empty, right? and dp minus 1, sorry, or the 4 is either the h is either small or equal than the dp minus 1. Okay, we do oh, probably not. Sorry. Forget about that, forget about that. It won't work because in this case we have a 10 and 2 here, right? But we don't want to pop this 10 out because that will give us the actually that may also work, sorry, because we can update the answers every time when we have a number here. So which means we have an answer here, that's going to be 0. So we have a while loop here, right? While dp is stat, and then we do a dp dot pop, okay? And then here, sorry, I don't know if I'm doing something useful here or not. And so we have dp dot append h here, right? And then we every time we'll do update, we get a maximum of the answer dot the length of dp. In the end, we simply return the answer. I'm hoping this will also work. Yeah, accept it, submit. Hmm. Let's see. Okay, sorry, forget about what I said about the monocle. Just forget about it. So it won't work here. All right, guys. So that's it. Just stick with the DP and this binary search solution here. And cool. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.